All right, good afternoon, everybody. Welcome to Intro to Space Navigation Spring 2025, Lecture 20. And I'd like to start reviewing course map to be sharing, okay? This is Lecture 20. We are starting a new unit. So if we go back to our course notes, Lecture 16 and 19 was a 4-lecture series on star trackers. So we learned about, there we go, to the top. This is kind of the overview of the entire Star Tracker lecture series, but this is all that you need to do to survive and thrive on homework 4. There's kind of our mathematical model for how to treat a space camera as a navigation instrument, so how to go from lit pixels in an image that belong to stars to unit vectors in the camera frame. We learned how to kind of interpret a star map like the Hipparcos catalog, how to put together an index search problem to identify the stars in your image. And then finally, if you know the unit vectors for the stars in your image in the camera frame, but you know those same unit vectors in the inertial frame, then it's relatively straightforward to solve what's called Waba's problem and determine the orientation of the camera. So your final deliverable with all of this would be the attitude transformation matrix or the quaternion. I think I asked for the quaternion in homework 4, from inertial space to the camera frame. And that was the last unit. We're all done with that. So lecture 20, it's a bold new world. We are going to be talking about Kalman filtering, which is kind of an extension of our discussion of estimation theory. So in estimation theory, if you recall, we talked about uncertainty quantification. We talked about what covariance means. We talked about linear estimation problems, y equals hx, and how to solve problems of that type. So we learned about least squares, weighted least squares, maximum likelihood estimation. We even learned about something called batch estimation, where in batch estimation, we're trying to estimate the state of an object, usually a space vehicle, at one time, given measurements from several different times. And I kind of alluded during that lecture to another way of doing things, which really deserves its own unit, and here we are, which is how to, so kind of returning to an estimation theory framework, but now we're not handling the measurements all at once. We're kind of keeping a running tally of where we think we are, keeping a running guess, and that is Kalman filtering. So the little icon in the course map for Kalman filtering is not meant to be a robot head. That's meant to be my PowerPoint art rendition of the Apollo guidance computer, which was running the navigation software during the Apollo missions. And so same thing, like on the, generally missions that you send out to explore deep space, and I'm pretty sure even low Earth orbit, we'll be running some sort of a Kalman filter, some sort of sequential estimator to keep a running guess of its state. And we'll talk about how it does that. This is going to be a 3-lecture series where today we talk about what's called the propagate step. We'll learn about what the propagate step is today. And then the next lecture, we're going to talk about the update step. And those are the big 2 things, propagate, update. In the Kalman filter parlance, that's kind of like right foot, left foot. We just keep marching forward, propagate, update, propagate, update. We'll learn about those over the next 2 lectures, as well as some special kind of filter considerations. And then we'll learn about some advanced Kalman filter techniques like the extended Kalman filter. And if we get to it, the unscented Kalman filter will be in the following lecture. So that's lectures 20, 21, and 22. And then finally, our last unit after that will be optical navigation. So determining the position of a vehicle from information in an image, which is kind of a sisters with Star Tracker, which is determining attitude from information in an image, except now we're looking for position information. And so that'll be the unit that we spend the rest of the semester on. So optical navigation, we'll just keep going until we run out of lectures. But Kalman filtering, there will be 3 lectures. And I think if I look ahead at the schedule, there are 4 OpNav lectures, and then we're done. So for those of you that are doing the math at home, that's 7 more lectures in this class. So already the end is in sight. So let's talk about Kalman filtering. And I want to start with a road trip metaphor. So bear with me here for a moment. So this is Kalman filtering. or I'll say Kalman filters part 1. That's today's lecture. Okay. So we'll just start with a discussion, and anybody can key in their microphone and answer this question if you like to. Imagine that you are on a road trip. So most of you live in and around Troy, New York as RPI students. Let's say that you and a friend hop in a car and you decide that you want to drive to New York City for the weekend, or you want to go do a weekend trip to New York City. Now, generally, it takes what, maybe 2.5, 3 hours to drive from Troy to New York City, thereabouts, depending on traffic and all that. So let's say that you are driving and your friend is in the passenger seat and they're meant to be navigating. So they're meant to have their phone out and pull up Google Maps or take your pick navigation software. And you start driving, and let's say you get maybe 10 minutes on the highway, and your friend says, okay, in 5 minutes we'll be in Poughkeepsie, which those of you for kind of a geography lecture, Poughkeepsie is roughly the halfway point. It's a little bit closer to New York City than it is to Troy. So in that moment, when your friend says you're almost to Poughkeepsie, but you think, I've been on the highway for 10 minutes, who are you going to trust? And what's your thought process? Can you walk me through how you would handle that if you were the driver?
I mean, if I know I've been like, I mean, personally, admittedly, my internal clock is perhaps not the best, but if I know I've been driving for about 10 minutes, I know the range of speeds that my car can travel, and traveling at presumably almost airliner-esque speeds to Poughkeepsie, um, what is probably 50, 60 miles at
Mhm.
least. No, more than that, probably
More
100.
than that. Yeah.
I'm more likely to discard whatever my friend has said, and more likely to just trust my own intuition and me looking at the speedometer.
Yep. Very good. So this was actually a trick question, but the other way, because I would have taken any answer to this one. But that I agree with you. I would have said, man, is your phone upside down? Like, what's wrong? How could you be getting something that's that whack? But regardless of what your answer is, in that moment, you are exercising critical thinking to compare your mental model of the situation, which for me would be something like, I've been on the highway for 10 minutes. I'm driving about 60 miles an hour, which is about a mile a minute. So probably I'm 10 miles down the road. And when my friend says we're 100 miles down the road, I say no way. That's not likely. But you're exercising your critical thinking because you've got your intuition, like you said, or your mental model of the situation, but you also have new measurements coming in, and you're forced to make a decision. Do I go with my gut or do I go with the measurement? And in that moment, when you are making that decision, you are a Kalman filter, right? Now, instead, you might say, okay, you've been on the road for long enough that you honestly kind of forgot, or you don't really trust your estimate. You go, gosh, have we been driving for 20 minutes or 30 minutes? I don't really remember. Then you might be more likely to trust your friend and go, gosh, I really thought I knew where we were, but maybe I didn't. So, Kalman filters find the balance between instinct and observation, where by instinct, I mean some sort of internal physics model, and observation, I mean external navigation measurements. A Kalman filter, which we're going to use this term all day today, so we're going to start abbreviating it as KF. Kalman filter is an optimal state space model-based estimator. And if that doesn't immediately make sense, it will at the end of the lecture. Don't worry. Optimal as in from derivation, you won't find a better way of handling this problem than a Kalman filter. Now that said, there are many different variations on Kalman filters, and there are many different ways to tune your Kalman filter. But this is kind of the way to handle this type of problem. It's optimal state space, as in it takes in x, y, z, x dot, y dot, z dot, and then propagates those. Model-based estimator, so you do need some sort of physics model for how your system is going to propagate. There's already one of the two buzzwords, propagate and update. So you need some sort of model of your system in order to use a Kalman filter. This was invented in the 1960s by Rudolf Kalman. Sorry. I'm getting this mixed up with the von Karman line. Is it F? Yeah, it's F. Rudolf Kalman. And used in the Apollo program. And today. So Kalman filter consists of two main steps. Propagate, which we'll be discussing today, and update, which we'll be discussing next time. Where propagate is the natural evolution of the state due to dynamics. And then update is the sudden change of the state because of new information. So imagine you're keeping a running guess of x, y, z, x dot, y dot, z dot. If you don't do anything, then that will drift, even if you're just accounting for orbital motion, right? You know that your system's not going to look the same in 10 minutes as it does now because of your physics model. But then all of a sudden, you power on one of your sensors, take a measurement, and you get something that isn't quite what you expected. Then you need to make a decision. That's that update step. So we'll get to that next time. So the classic Kalman filter assumes a linear dynamics model and a linear measurement model. So don't write this in your notes yet, but any table of dynamic systems or a similar class, and you get something that looks like x dot is ax plus bu, and then y is cx plus du, something like that, that state space representation of the system you're trying to control. Don't write that down, because that's not what we're doing today. What we're doing is pretty daggone similar, though. So x dot is, oh, you know what? Sorry. X dot of t is equal to f of t, x of t, plus g of t, omega of t. And then y tilde t is going to be h x plus nu. Where, okay, let's start explaining things. X is your true state vector. And then omega is zero mean white process noise. And then y tilde is your noisy measurement vector, which it can just be a scalar, vector or scalar. And then nu is your zero mean white measurement noise. So nu is, this is going to sound like a terrible pun. Nu is nothing new because we've seen this before. We saw this all the way back lecture, this was lecture 10. It was lecture 11. There it is. Yep. This is the same nu from lecture 11, right? We have a noisy measurement, which is some function of our state. And in this case, it is just a linear y equals hx. But then there's also some measurement noise that we need to account for, and that's nu. Similarly, our state updates x dot equals fx plus some g times omega, where omega is some state noise, essentially some state dynamic propagation noise, which we call process noise. So this is the new guy, and then nu is nothing new. And let's take a moment, and we're going to do a quick aside about what I mean by noise and measurement noise. So quick aside, noise. So white noise, which we've already been working with for a good chunk of the semester, is a stationary stochastic process. Where by stochastic, I mean evolves randomly over time. But then by stationary, I mean that the probability distribution does not change. Or we could say is invariant to time. So you might be saying, well, I thought that this was a random number. How can it be stationary over time? It's like, well, it is a random number. Every time you analyze this random number, it's sort of like going back to that kind of classic, grade school example of drawing marbles out of a paper bag. It's like, it's the same paper bag over time. You're just pulling a different marble every time you analyze it, that sort of thing. So it's not the same random number every time. It's the same distribution of random numbers every time. But you pull an actual different number out at every instantiation of this random noise. And no matter how fast we sample white noise, it is truly random. Now, white noise does not exist in reality. But is a useful mathematical construct. So in our dynamics model, G of t omega of t describes the noise that corrupts our dynamics. We call this process noise. So here's a diagram, which is one of my favorite Kalman filter diagrams. Hopefully this makes things make sense for spacecraft. And I'm going to do my best here. Okay. Go. And then let's say it's got a little nav sensor here. And let's say that it's got its solar panels, which this is not exactly what Orion looks like, but it's close enough. And then it's got its little engine. There we go. And rather than drawing this thing 3 times, I'm just going to do this because I'm lazy. Go. Now, as your spacecraft is floating along, you run into the situation where over time, you are going to be less and less and less sure where it is. Is it going this way? Could it be maybe drifting this way? Could it be maybe drifting this way? The same way that as you're driving down the road, you're less and less and less sure where you are until it takes some type of a measurement. So the little signal coming out of its sensor is saying, oh, it actually takes some type of measurement here. So let's be clear. This is a nav sensor. This would be looking at a road sign, looking at the map, looking at your GPS, that sort of thing. All of a sudden, you lock in where you think you are. You have a much lower uncertainty. Not necessarily zero uncertainty, because there's always going to be some uncertainty, but your uncertainty will plummet in an instant. And then it will immediately start to grow again. You'll go, okay, pretty sure I know where I am. But then as you drive, you're going to be less and less and less sure, less and less and less sure. Am I going this way? Am I going this way? And then you take another measurement, and so on and so forth, and you lock in your knowledge of where you are. So in the moment that you are taking a measurement and processing that measurement, then you are dealing with measurement noise, which is new, right? But in between measurements, as you're letting your state propagate, then you're not really sure which way your vehicle's going. I mean, you have a good idea, but there's going to be some uncertainty. That is where process noise reigns, or omega. And then you take a measurement, and again, you're dealing with measurement noise. And then process noise. And you're starting to see the pattern here. Now, you'll frequently see, especially in some visualization of our uncertainty over time. So let's say that you are really pretty sure, and let me do this. Can I draw just a straight line? Oh yeah, now we're cooking. Okay. So let's say that this is 0 error. So you're graphing your uncertainty in your state over time. So let's say at some initial time, think in terms of error bars, right? You think, okay, I think I know my error. I think my error is 0 in my state, but my uncertainty is that I'm somewhere within this error bar. So you're carrying around some x, y, z, x dot, y dot, z dot. You think you know what your state is. Let's just focus on one of those states. Let's just say your x position, right? So it's a one-dimensional problem. What I'm saying on this, and we're going to fill this graph in a second, it's going to make more sense, is that if I subtract the state that I have from truth, which I don't know, you'll never really know truth, you just get as close as you can, then I'm really pretty sure my answer is within these error bars. And then what's going to happen is those error bars are going to grow, get worse and worse and worse, like so. And then all of a sudden, you take a measurement, and your error bars just crash down. And you go, oh, I think I know exactly where I am. And then slowly over time, and it's kind of exponential, your error bars are going to get worse and worse and worse again, just like this. And then all of a sudden, you take and it comes crashing down. Try to make this symmetrical as best I can. This is going to be a symmetrical graph, right? And then slowly over time. Kind of looks like the barrel of like an old-timey blunderbuss from the 1800s. Slowly over time, your error bars are going to get worse and worse and worse. And then you take a measurement and they come crashing down again. And then so on and so forth, right? It just keeps going. Where this is a graph of your uncertainty. Where here you are propagating. In this instant, we update. And we propagate. Then we update. Then we propagate. Then we update again. And this goes on until the mission's over or your computer fails. So never ending. So that is kind of our visualization of like, okay, between measurements, our uncertainty is creeping up. And then you take a measurement and your uncertainty plummets. And then slowly it creeps up again. And you're always going to be in this cycle of more uncertainty, less uncertainty, propagate, update forever and ever. So if you find yourself in a situation where your process noise is negligible compared to your measurement noise, that is to say, you really just don't trust your measurements, you really trust your dynamics on board, you're going to end up in a bad situation, right? What we have is a Goldilocks problem here. If you let the process noise get way, way small compared to the measurement noise, you will ignore your sensor. You'll say, you know what? I don't actually need to know what my sensor is saying. I don't trust that piece of junk anyway. I know what I'm doing. And the actual technical term for this is a smug filter. It's a filter that's no longer even asking for updates. It's just going to keep doing its own thing. However, if your process noise, if your uncertainty in your dynamics is much, much larger than your measurement noise, then you would have no reason to trust your model. You would ignore your dynamics. And then you just would have a measurement pass-through situation where you say, okay, whatever new measurement comes in, I guess you're right. I guess I really am at Poughkeepsie, even though it's only been 10 minutes. I trust you because I don't trust myself. So there needs to be a healthy balance of, do you trust yourself or do you trust your friends with their phone? Or do you trust your dynamics or do you trust your measurement model? So Kalman filtering is a continuous Goldilocks problem. Okay, questions on Kalman filters so far? We've kind of, that's the end of the introduction, and it's about to get kind of mathy. Good stuff? Okay, cool. Actually, you know what? If I'm going to be brutally honest, I think the next two lectures are going to be some of the most dense math we're going to do in this class. So buckle up. Here we go. We're about to talk about state and covariance propagation. Okay, so we begin with our dynamics model. Which is, remember, x dot of t, I always forget of t, is f of t, x of t, plus g of t, omega of t. Omega is our process noise. G maps our process noise onto our state derivative. X is our state. F maps our state onto our state derivative. So this is kind of like the AX. And then this is not quite BU because in a modeling control of dynamic system standpoint, U is control input, where here it is just a random number. So that's our dynamics. So this is a first order differential equation. It's actually a first order stochastic differential equation. And we can solve it, or we at least know it has a solution of the form x of t is equal to phi t naught x of t naught plus the integral over time from some initial time to the current time of phi t epsilon g of epsilon omega of epsilon d epsilon, where this first term is just simple dynamics and this second term is what accounts for noise. So basically, the integral of random noise is the term on the right. And we also know that a dynamic model of the form x dot equals fx is going to have a solution of the form x equals phi x, where phi is the good old-fashioned state transition matrix, which we all made homework to. It is back again to help us. Where phi from t naught to t is the familiar state transition matrix. Which, as a reminder, behaves according to phi dot from t naught to t is f of t phi from t naught to t, and phi from any time to itself is just the identity matrix, n by n. So we assume that omega of t is zero mean white noise. So not the type of white noise that you listen to go to sleep, but white noise meaning that it's a random number that is completely uncorrelated with itself over time, which is completely different than that first order Gauss-Markov process we talked about. How many lectures ago was that? Oh, it's been a minute. But I remember, I think that was in our, was that the, yes, the inertial navigation lecture. We talked about, we treat our gyro bias as like a random walk term, which has a natural tendency to kind of march itself back to the origin, but then it wanders off again and then marches itself back to the origin. This is not that. This is truly a random number, or as close as you can possibly get. So the random number at some time t, 1 nanosecond later, is going to be completely uncorrelated. Right? So the way we would express that mathematically is the expected value of our noise is going to be 0. And the expected value, if we were to take this noise at some time t and then multiply it by itself at some future time epsilon, then what we would find is this would be some q of t delta t minus epsilon. Okay, so let's make that make some sense. So q of t is going to be a, so remember we have our measurement noise or our measurement covariance, then we have our process noise covariance, that's q. So q is friends with r from homework 2. But then we have this delta here. So let's say where t is some time, epsilon is some other time, And this delta is the Dirac delta function. Which is, let's see, returns 1 if input is 0 and returns 0 otherwise. Okay. So we could express that in plain English. Or plainer English. The expected value of omega of t transpose is Q of t, which is going to be our process noise covariance matrix. But the expected value of omega of T1, any T1 times omega of T2, any other T2 is 0. So it needs to be the same time. Noise is only correlated with itself at the same time. It is uncorrelated otherwise, right? That is a key assumption in our derivation, which as we work our way through the Kalman filter derivation, we will use that moving forward. Okay, so we have a solution of the form x of t is phi times x, where phi is the state transition matrix, plus this integral, which accounts for our noise. And we kind of went off and we just said, okay, by the way, this is what we mean by phi. By the way, this is what we mean by omega. Okay, great. It's time to revisit this equation here, make this make a little more sense. By the way, throughout this derivation, there's going to be more stop and explain checkpoints than usual. I hope you don't find that annoying, but there's going to be a lot of equations. So trying to make each step of it make sense if we can manage it. Okay, so the expected value of our state is expected value x of t is equal to expected value, and then we have phi t naught to t x of t naught plus integral t naught to t phi from epsilon to t g of epsilon omega of epsilon d epsilon. So what is the expected value of all of this? Well, the expected value of anything that isn't random, you can just skip it, right? So here, x of t expected value is phi. We know what phi is, right? We're not confused about our dynamics. We just know that there's noise on there. So we'll keep expected value of x naught. Going to abbreviate x of t naught as x naught plus the integral t naught to t. Let's think about it. Phi, again, we're not confused about. It's not stochastic. G, the matrix, which we're not super familiar with G yet, but G is the matrix that maps our noise onto our derivative of our state. Nothing about this is like noisy. The noise is all right here. So expected value of omega of epsilon, the epsilon. Okay. However, the expected value of our noise is 0. So you might have been able to guess this. The integral term of our noise to work out to 0 because we've got random noise. Sometimes it's positive, sometimes it's negative. In the aggregate, it should work out to do basically nothing. So what we can say is the expected value of our state in the process of white noise is just going to be phi t naught to t expected value of our initial state. There we go. So this is an important intermediate result that we will be coming back to. Okay. Now turn our attention to covariance. So let's see. Oh, good. Okay, I should be clear. I'm looking at my notes and I realize this does not get a black box. This gets a red box. This is more important. This is actually it. The thing is, in our filter, I know I can, you know what, here. Let's just do this. We do a rectangle. Yes, there it is. Where this is our measurement, sorry, is our state propagate step. Okay. So if you have a guess of your state at some time, then your best guess of your state at a current future time is just to multiply by the state transition matrix. And the covariance is going to be a little bit more complicated, but we'll see how to proceed with that. But yeah, so we're talking about its propagation. This is our state propagation equation. Okay, so we now turn our attention to covariance. So as a reminder, the state covariance P, which describes how much we're not sure about our state X, is the expected value of, and then we've got our state minus the expected value of our state, and then our state minus the expected value of our state. Oops, I always forget of T minus the expected value. I'm just all over the place today. Sorry about that. Minus the expected value of our state, and then transpose. Okay, so state minus our expectation, transpose, expected value of all of that. That is by definition our state covariance matrix. Okay, now we can actually go through and multiply this out, and what we'll get is the expected value of x of t transpose minus the expected value of x of t times the expected value of x of t transpose. Okay, so if we have both of these two terms, then we can say what our best guess of our future covariance is. So we will focus on the first term for now. Okay. So, the expected value, and if I start my equation over here, you know we're taking up the whole line. Expected value of x of t transpose is equal to the expected value of, okay, let's think about it. If x of t is this business, right, phi x plus integral term, we're basically going to have to do that twice. So it's going to be phi from t naught to t, x of t naught plus integral from t naught to t, phi of t epsilon, g of epsilon, omega of epsilon, d epsilon. So that is x of t. And then we've got x of t transpose, which is going to be phi from t naught to t, x of t naught. And want to be clear that we're doing a different integral, so we're going to have a different term here. We're not integrating over epsilon, we're integrating over eta. So phi from eta to t, g of eta, omega of eta, d eta, transpose. And that's the expected value. So we've got x of x transpose. And we're using a different term here just to be clear that this is not the same integral as before. Okay, so now, what do we do about, well, this is going to be expected value of, and then the first term is going to be the same. In solidarity, I'm going to write all of this again because we all have to, but this is phi t naught to t, x of t naught plus t naught to t, phi epsilon to t, g of epsilon, omega of epsilon, d epsilon, close parentheses. And then now we're applying our transpose. So this is going to end up being the integral from of omega of eta transpose, g of eta transpose, and then we've got phi from eta to t transpose d eta. So remember that when you have like A, B transpose, you get B transpose A transpose. So the transpose distributes and you switch the order. That's why we've switched the order here. Plus, following that same logic, X transpose of T naught, and then phi from P naught to T transpose. Okay, and then close and close. Yep. Okay. So if we distribute, things had better start canceling out pretty soon because this is getting pretty ugly and my wrist is going to get tired. So next terms and apply the expected value operator. Okay, so believe it or not, this gets worse and we're no longer going to be able to fit it on one line, but things are going to start to get a little bit nicer. So expected value of x of t transpose is, okay, first term times, in this case, the last term. It's going to be a kind of a variation on FOIL. It's going to be just our state transition matrix term. So phi t naught to t, and then we've got the expected value of x of t naught, and then x of t naught transpose, and then phi t naught to t transpose. And I guess half the time I do my transpose before of t and half the time I do it after. I don't think it makes a big difference. As long as we're clear what we're talking about, it's the same thing. First, okay, then we're going to have the two middle terms, right? Like kind of the two AB terms, right? So we'll have phi t naught to t of the integral from t naught to t, and then the expected value operator. So we're skipping some stuff, right? Expected value operator only applies to the state and the noise, so we can skip all the other things. And when we multiply in x of t naught, so we're basically looking at phi times x multiplied by the integral with all the transposes, the eta integral. So phi will stay outside the integral, x will multiply in. We'll get expected value of x of t naught times omega of eta transpose. And that's the only bit that's inside the expected value operator because g of eta is not random. And then phi from eta to t is not random, the eta. Okay. And then our next term is going to be plus, so it's going to be the other way around. Now it's going to be the integral term with all of the epsilons multiplying x transpose and then phi transpose. And I think I have a mistake in my handwritten notes. Let me just fix that. There we go. Okay, apologies. Just derailing myself here. So this is going to be integral term first, t0 to t, phi from epsilon to t, g of epsilon, and then we've got the expected value operator, which acts on omega of epsilon, and then x of t naught transpose the epsilon. oh wait, before I do that, not d epsilon, apologies. Then we've got phi of t to t naught transpose d epsilon. Okay, so those are our inner two terms, and then we've got our last term, which is going to be the double integral, the dreaded double integral here, which is integral from t naught to t, integral from t naught to t, phi epsilon to t, g of epsilon, expected value of omega of epsilon, omega of eta, transpose, and then we've got g of eta, transpose, phi from eta to t, transpose, d epsilon, d eta. Okay, so please tell me that something in here cancels out, because this is now a 4-line long equation. And the answer is yes, it does. The expected value of x multiplied by omega. So this might seem like gibberish, and that's because it is. There is no correlation between your state at the initial time and your random noise at some time eta, right? So this is equal to 0 because we've assumed white noise. Yep. Similarly, by symmetry, this is 0 because of white noise. So we can drop 2 terms. And then our final term is, remember, the expected value of omega omega transpose is 0 in general. It's q of t only when the 2 times. So I'm going to take this and I'm going to rewrite this as q of epsilon and then Dirac delta epsilon minus eta. So when epsilon and eta are 2 different times, which is in almost every case, this final term can be canceled out. In the time that we're saying, oh, I want the kind of self-correlation, I want omega's correlation with itself, then we return q. Okay, so we haven't quite answered the question. Remember, kind of getting a little bit into the weeds. Expression for what is our p of t over time. So what is our new covariance over time, right? We're tracking our best guess of our state and we're tracking our covariance. We are still waist deep in this first term. Then we've got to figure out that. Let's continue with 2 neat properties of the Dirac delta. Okay. The first is that the integral from negative infinity to infinity, Dirac delta t minus tau d tau equals 1. So kind of by definition, the integral forever to the left, forever to the right of Dirac delta is equal to 1. And integral from negative infinity to infinity of some function times Dirac delta t minus tau d tau is equal to just the function. Okay, so therefore we can simplify greatly, which is really nice. So we're back down to 1 line now. The expected value of x of t, x of t transpose is equal to, so it's going to be the first term, right? Phi from t naught to t, expected value of x of t naught, x of t naught transpose. You might be thinking, this kind of almost looks like an expression for our initial covariance. Not quite, but you're thinking along the right terms. So we are ultimately going to express our future covariance as a function of the initial covariance, the state transition matrix, and a whole bunch of integrals. Okay, and then this is phi t naught to t transpose. So that's the first term from above. And then we've got the last term, which is going to drop from a double integral to a single integral because of this Dirac delta property. So we've said that the integral forever of a function times Dirac delta is just the function. So we can drop this to the integral from t naught to t of phi epsilon to t g of epsilon q of epsilon g of epsilon transpose phi epsilon to t transpose d epsilon. Okay, so we can plug this back into our expression for covariance. Okay, so remember we said that is expected value of XX transpose minus expected value of X, expected value of X transpose, right? So we'll just go through and pop this in like so. E T, okay. It's gonna be phi T naught to T, expected value of X of T naught, X of T naught transpose, phi T naught to T transpose, plus the integral T naught to T, phi epsilon to T, G of epsilon, Q of epsilon, G of epsilon again, phi epsilon to T transpose. Oh, and this is transpose as well. D epsilon minus the expected value of X of T times the expected value of X of T transpose. Okay. But from before, we just said that the expected value of X of T is phi, other way around, T naught to T times the expected value of X of T naught. Okay, that was our result from before. That was our state propagate step, right? Just plug that in here. And so if we do that, we get what might be, well, I guess we had a 4-line equation before, but this is about to get kind of gnarly here. We get P of T is equal to phi T naught to T, expected value of X of T naught, X of T naught transpose, phi T naught to T transpose, plus the integral T naught to T, phi epsilon to T, G of epsilon, Q of epsilon, G of epsilon transpose, phi epsilon to T transpose, D epsilon, minus, okay, this is going to be the phi from T naught to T, expected value of X T naught, but then we've got expected value of X of T naught transpose, and then phi T to T naught transpose. Okay, now, as this is, we've reached kind of the top of the mountain. Things are about to cancel out, and things are about to get a little bit easier to work with here. So this is pretty much as bad as it gets. This first term is state transition matrix times some stuff times state transition matrix transpose. And the last term is state transition matrix times some stuff times state transition matrix transpose. So we can combine the first and last terms. Okay. So we get P of T is phi from T naught to T. And then we've got expected value of x of T naught, x of T naught transpose, minus the expected value of x of T naught, expected value x of T naught transpose. And then all of this multiplied by phi from T naught to T transpose. And then we've got our integral term, which I'm not going to copy paste. I'm going to write it out in solidarity, is phi from epsilon to T, G of epsilon, Q of epsilon, G of epsilon transpose, phi epsilon to T transpose D epsilon. Okay, here is where things get pretty nifty. So remember, our definition is expected value of state transpose minus expected value of state transpose. That is this term. This term here is simply the covariance of our initial state. So thank goodness we finally have made some progress. We can say, and as a matter of fact, this is pretty much our final equation here, that our covariance at some time t is related to our initial covariance by the state transition matrix. So T naught, P of T naught, B, T to T naught. And then there is our nasty integral term. Sure, you were hoping this would cancel out to 0. It doesn't. B, T epsilon, G of epsilon, Q of epsilon, G transpose of epsilon, B, T of epsilon transpose, D epsilon, where this gets a red rectangle. Yes, like that. There we go. Where this is our, so we've talked propagate. This is our covariance propagate. And before we move on, I will summarize and also compact our notation, because frequently we are not moving from initial time to final time. We're moving from one time increment to the next time increment, right? So let me summarize. Okay. I'm going to say that the expected value of x at some time tk is phi from tk minus 1 to tk, so just incrementing forward one time step, times the expected value of x at tk minus 1. And our p of tk is phi TK minus 1 to TK, P, TK minus 1, phi, TK minus 1 to TK transpose, plus the integral from TK minus 1 to TK, phi, epsilon to TK, G of epsilon, Q of epsilon, G of epsilon transpose, phi transpose, phi epsilon, where this integral term is often abbreviated as QK, which is not the same thing as Q of epsilon. So Q of epsilon is the process noise covariance matrix. It's related to R, where R is the measurement covariance matrix, or process noise covariance matrix. But then there's QK, which is the term which describes the integral of the noise between two time steps. And while they are both Q, they are not the same Q. So great opportunity to get things a little bit confused. BK, by definition, this is just B that maps from the previous time step to the current time step. Okay. So now we can say, and this is the one to really write down in box, that the expected value of x at sometime tk, which remember, we don't track our state, we just track our best guess of our state. So this is our state propagate. Well, that's just going to be phi k, expected value of x tk minus 1. And our p, we'll just say pk, is phi k, p k minus 1, p k transpose plus q k. Great. Okay, one more red box just to summarize everything, like so. And that's it. So in practice, what we'll be looking at is something that looks a little bit more like this, rather than what we saw with kind of the gnarlier equations. So this is closer to what you'll actually code up. Now, we're going to go through a lot of different steps and a lot of different, we'll go through some examples and all that to make this make a little bit more sense. But I think we've been going pretty hard. This is a good natural stopping point. So we'll pick back up in about maybe 5 or 6 minutes. So it's 7:11 for you. So why don't we say break back at 7, say 16. Apologies, lost track of the time there. All right, so we just got a little extra break, but maybe we need it. There's kind of a lot of math going on today. So realize this is kind of confusing. It's going to stay confusing. We'll kind of summarize all of the Kalman filter stuff towards the end, and we'll hopefully make a bit more sense. But just for now, I hope our grasp on the situation looks something like this. We will start at some initial time with some initial guess of our state and some initial covariance, and we can propagate those forward. We could say, okay, at the next time step, my best guess of my state is this, and my best guess of my covariance is this. And clearly the heavy lifter here is the state transition matrix, which we talked about before. So we're kind of somewhat friends with the state transition matrix. And then there's this new character QK, which is going to make a little bit more sense as we move along. So this is the of doing your state and covariance propagation, but there is another way that you should be aware of. So I'll teach it to you, and you can do it on the homework if you want to. By the way, homework 5 is coding up your own Kalman filter. So that's where we're going with this. So we'll be talking about state and covariance, propagation, alternate method. Let's just try to draw a straight line, shall we? That'll do. Okay. This is not recommended. But it'll work. This is what I've heard referred to as the down is not the preferred way of doing things. These equations will get you there, but you're definitely cutting some corners. So we may also write state and covariance propagation as differential equations. Okay, so you could say x dot t is equal to f of t, x of t plus g of t, omega of t. Okay, where the expected value of x dot of t is equal to f of t. Let's try to make this dot a little bit cleaner here. Expected value of x of t. So here we're not actually solving for x of t as a function of previous time. We're just saying, okay, I'm comfortable with this existing as a differential equation. And then you've got g of t expected value of omega of t, which this term is equal to 0. So you can drop the whole second term. So we can just say that the expected value of x dot of t is f of t expected value of x of t. Okay, so we're just saying that our derivative of our best guess of our state, or the best guess of the derivative of our state, it propagates forward the same way that our state would propagate forward in the absence of noise. So our best guess is that the noise doesn't really make a difference in the long run, so we just ignore it. Right? So this is just the differential equation version of the propagate step that we saw before with the state transition matrix. So maybe I can just try a regular old rectangle for this one. There we go. So this would be our state propagate differential equation. Okay. And Okay, where, okay, remember, P of t is phi t naught t, P of t naught, phi t naught t transpose plus t naught t, phi t epsilon, g of epsilon, q of epsilon, g of epsilon transpose, phi t epsilon transpose, d epsilon. Okay, we want p dot. So time for some calculus. Okay, so you might be thinking, okay, we're about to take a derivative. Surely this integral is just going to neatly cancel out. No. Okay, so bear with me here. The derivative, so we're going to say p dot of t is equal to, okay, we find ourselves in a like first times derivative of second plus second times derivative of first and all that. So we're going to say, okay, this is going to be phi dot from t naught to t, p of t naught, phi t naught to t transpose, plus the p dot t naught term is not going anywhere. That's going to be 0 because the covariance at the initial time, we can leave that. We're going to say that this is phi of t to t naught, p of t naught, phi dot t naught to t transpose, plus, I'm not going to bother writing it all, but this is the derivative of the integral term. Just because we're going to rewrite this again in a second. So how do we take the well, remember Leibniz's rule. So remember, when Isaac Newton was inventing calculus, Leibniz was also inventing calculus around the same time. So Leibniz. And he said that, we're going to be able to use this in a second here. The derivative with respect to alpha of a of alpha, b of alpha, some function of x and alpha dx. So we're taking an integral, which is an integral with respect to time, and then we're taking the derivative of an integral with respect to time. But it's not quite so simple as just dropping the integral term. This is equal to db or dA f of b alpha minus dA over dB f of a and alpha plus the integral from a to b d of d alpha f of x and alpha dx. Okay, so let's use this to try to make the derivative of the integral term just a little bit cleaner. So let's start by writing out the left-hand side of the equal sign. So therefore, we have what? It's the derivative with respect to t of the integral from t naught to t of phi epsilon to t, g of epsilon, q of epsilon, g of epsilon transpose, phi epsilon to t transpose, d epsilon. Okay. And this is equal to what? Okay, so it's the derivative of some time term to some other time term. So we would write this as dt over dt naught. And then we've got the function, the whole integrand of alpha and b. So we would write this as phi from t to t, g of t, q of t, g of t transpose, and then phi from t to t transpose. Okay. Then, so just going to say right now, this is equal to 1. This is equal to identity. This is equal to identity. Okay. So that's the derivative of time with respect to initial time term. Then we've got a derivative of initial time with respect to time term. And I'm not even going to bother writing it out to save you time because this is 0. The derivative of the initial time to time is 0. Okay. Then we've got the integral, but now it is from t naught to t of, we can take the derivative. So derivative with respect to t of b epsilon to t, g of epsilon, q of epsilon, g of epsilon, b, epsilon to t, transpose d epsilon. Okay. So let's inspect this last term here. So we have the integral of the derivative of a bunch of stuff. So how is this going to play out? Well, it's going to be another for the first times the second. Oh, yes, Michael, question?
Not sure if it's a typo, but should the second g in that integral term be a transpose or not?
I was just seeing who's paying attention. I didn't make a mistake. I'm just kidding. Yeah, good job. Okay, cool. Thank you. So the second term is going to be one of those 1d2 plus 2d1 deals. So let's look more closely at the last term. So this is the integral from t naught to t of phi dot epsilon to t, and then the rest of it stays. So g of epsilon, q of epsilon, g transpose of epsilon, phi t epsilon transpose, plus phi t epsilon, g of epsilon, q of epsilon, g transpose epsilon, and then here's our phi dot t epsilon transpose, and then close d epsilon. Okay, the reason we're writing this all out is we're about to make a cool substitution. So we'll say, now recall that phi dot is f phi. And by that same logic, phi dot transpose is going to be phi transpose f transpose. So we can substitute. Okay. All right. So where are we? We are actually at this equation right here. That's where we are. So we're saying p dot of t is phi dot p naught phi transpose plus phi p naught phi dot transpose plus the integral of all this stuff, which we just said is 0 plus this term, and we're about to start to simplify everything. So we're bringing it all together into one equation again. So P dot of t is equal to f of t phi t naught to t, p t naught, phi t t naught transpose, plus phi t naught to t, p of t naught, phi t naught to t transpose f transpose, plus we've got this term up here, 1 times I times G Q G transpose. So we get G of T, Q of T, G of T transpose. Okay. And then we get F times our whole integral, F of T. Because remember, phi dot is really F phi, and the F can be taken outside the integral. So this becomes F and then integral T naught to T. But we're going to get really tired of writing this integral before long. Also, we're like almost done for the day, so we're wrapping up soon. T of epsilon, G of epsilon, Q of epsilon, G of epsilon transpose. Oops, getting tired. That's not a Q. That's T of epsilon transpose D epsilon. And then there's one more term, which is integral T naught to T, B T epsilon, G of epsilon, Q of epsilon, G of epsilon transpose, B T epsilon transpose, D epsilon, all of this transpose. Okay. This is now, I mean, it is an equation that fills more than one line, but it's only 5 terms, right? And we can actually start to combine like terms. So let's combine terms by f of t. Okay. So we've got f of t times some stuff, which is the first term, but the fourth term is also f of t times some stuff. The second term is some stuff times f of t transpose. The fifth term is some stuff times f of t transpose. And only GQG is the term with no f's in it. Okay, so P dot of t is f t curly bracket, and it's going to be the first term and the fourth term. So t naught to t, P of t naught, phi t naught to t transpose, plus the integral t naught to t, phi epsilon to t, G of epsilon, Q of epsilon, G of epsilon transpose, phi epsilon to t transpose d epsilon. So that is our f times some stuff term. And then we've got our some stuff times f of t transpose, which, if you look closely, it's the same thing, right? The first term and the fourth term and the second term and the fifth term are going to be the same thing. So out of laziness, I'm just going to write like it's the same term because my hand's getting tired. And then finally we have plus G T U T G of T transpose. And here's the thing, this middle term, which Paul is feeling too lazy to write right now, if you look, is just P of T. Which means we can massively simplify this problem and say P dot of T is F of T, P of T, plus P of T, F dot of T. Sorry, whoa. I don't know where a dot came from. I'm getting tired. There we go. It's F of T, P of T, P of T, F of T transpose, plus G of T, Q of T, G of T transpose. And this gets us the derivative, right? So once again, we're not actually solving for P, we're solving for P dot. So this is our covariance propagate differential equation. Okay, so we would use this covariance propagation and state differential equations, basically using ODE 45 for ODE int. Right? This is going to be less accurate in the long run than actually just going through and computing the state update, or the state propagate, the kind of quote unquote preferred method. But this will still get the job done. So here, at each time step, we just compute the derivative of the expected value, compute the derivative of the state, and then we just feed those into something like ODE 45 or ODE int. Now, to use the what I call the ODE int method, we first need to vectorize P. For propagation. Basically, we just take the elements of P and then we align them up into a vector, because ODE int will propagate a vector, not a matrix. All right, and that's that. So we've now learned two different ways to propagate your covariance and your state, where, as a reminder, scroll up today, this is what we're talking about. So you've got your spacecraft. If you don't take any measurements, then over time, you've just got a dynamic model of how your system is going to behave, and you are propagating according to that, saying, okay, I think I know how fast I'm driving. I think I know how long I've been driving. I've got a hazy idea of where I am, right? That is propagation. It's the state transition matrix, which has all of your lovely dynamics baked in, to map from some old guess of your state to a new state. And you use the state transition matrix plus this nasty integral, which takes into account the noise over time. This E covariance is basically what we're plotting here, right? So if we had said, oh, I'm going to ignore the noise, then we wouldn't get this growth in uncertainty over time. The noise is actually kind of the star of the show with the Kalman filter, because that's really what we're trying to keep track of, is our growing uncertainty, which then next class we'll talk about when the time comes to update. All of a sudden our uncertainty collapses in an instant. We go, oh, okay, I think I know where I am again. And then slowly over time it gets worse. Bit much, we are building a foundation, and by the end of lecture 3, we will know everything that we need to know to code up our very own Kalman filter, which is homework 5. I'll give you range, rate, and bearing measurements of a spacecraft over time. Never enough information to get the state at one time, like at the same time. But if you code up a sequential estimator like a Kalman filter, then you can get a kind of a running tab of how accurate your not only your estimate of your state, but also your uncertainty, saying, well, I think I'm here, but I'm sure I'm within this bubble. That's where we're going. So any questions about Kalman filter propagate, or are we good to stop for the day? Cool. All right. I'm going to stop the recording, but I'll stick around in case anybody wants to chat for any other reason. But yeah, thanks everyone, and class is dismissed.